Look inside the human body at this exact second, and you'll find that millions of microscopic cells are on the move. They are squeezing through tissues to heal cuts, arranging themselves to build embryos, or, in the worst cases, spreading cancer. A resting cell somehow determines the exact moment to wake up and tear through its environment. For a long time, the assumption was that a chemical signal arrived, like a telegram, delivering explicit instructions to get moving. That model ignores the physical reality. These cells are suspended inside the extracellular matrix, a dense, three-dimensional web of protein fibers. And this matrix is an active mechanical partner, reacting to the cell in real time. Whether a tumor stays safely contained or invades surrounding tissue depends on a direct physical dialogue between the cell and the fiber surrounding it. To understand this physical dialogue, we have to isolate the mechanics of the environment. First, the matrix exhibits a property called strain-stiffening. Think of a biological polymer fiber like a loose rope. When a cell tugs on it, the slack disappears. The harder the cell pulls, the tighter and more rigid the entire surrounding web becomes. This chart shows the elastic modulus, a measure of stiffness, plotted against physical strain across different networks. As strain increases, the stiffness curves rocket upward. Look specifically at collagen and fibrin. These structural networks hold human tissues together, displaying extreme, nonlinear stiffening responses. The second mechanical variable happens inside the cell itself. This is mechanosensing. This plot maps traction force against environmental stiffness. As substrate stiffness on the x-axis increases, the cell exerts significantly more force. Following the trend line, there is a steady climb. The harder the floor, the harder the cell pulls, until traction reaches a saturation point. Putting these two variables together creates a trap. The cell pulls, which stiffens the matrix. The stiffer matrix cues the cell to pull harder. It is a closed, compounding mechanical loop. The physics question is what happens when these two escalating forces collide inside a closed system. The mathematical outcome of this feedback loop is bistability. Two stable states exist, separated by an unstable boundary. At the bottom is the low traction state. Here, the matrix is soft. The cell rests, generating little force. This represents dormant tissue, or a contained tumor. But biological environments are active. As fibers cross-link or surrounding cells increase tension, the matrix stiffness rises. As tension crosses that unstable threshold, the cell loses equilibrium. It snaps violently upward into the high traction state, generating maximum force. This isn't a gradual ramp-up. The transition happens all at once, committing the cell to its mobile, aggressive state. When that snap occurs, a quiet mass of cancer cells suddenly grips the surrounding tissue wall and tears itself forward. This physical jump provides the exact mechanical force required for a tumor to invade healthy organs. Once the cell makes this transition, the system uses its final survival advantage, hysteresis. This chart maps a hysteresis loop, which gives the cell a form of mechanical memory. The route the cell takes to jump up to high traction is separate from the route required to come back down. Because of this offset, if the cell moves into an area where the matrix stiffness drops slightly, it does not immediately revert to dormancy. It remains locked on the upper path, maintaining its aggressive behavior despite the softer environment. The dead scaffolding of our tissue dictates the physical forces behind our most critical biological behaviors. If you want to see us break down the hidden physics inside the human body, hit the like button, subscribe, and let us know what biological mysteries we should cover next in the comments. Today's video was brought to you by Synestex Systems LLC, founded by Shane Persinger.